Well, we have discussed about first order reversible reaction, then first order consecutive reaction, then first order parallel reactions. Okay, we have also discussed about the determination of order of reactions, how to find out the order of reaction. We have discussed about this. Now let us discuss another thing which is very important and interesting. Okay, so let us talk about reaction mechanism. Reaction mechanism. Okay, so you have studied about reaction mechanism in organic chemistry. Okay, so in organic chemistry, how we represent reaction mechanism? Say we represent by using some arrows. Say how the electrons are transferred, like that. Okay, we will be using some arrows to see the shifting of electrons. Okay, so in organic chemistry we use arrows, either a full arrow or maybe half arrow. Say maybe half arrow, say this, like this, to indicate the shifting of electrons. Okay, and that is how we represent reaction mechanism in organic chemistry. But in physical chemistry, okay, in physical chemistry, reaction mechanism means sequence of elementary steps. Okay, you say sequence of elementary steps. Let me give an example. Suppose this is the alkyl halide. Okay, this is the alkyl halide. Okay, this is the alkyl halide, and aqueous potassium hydroxide is reacting. So what we get? We get this plus this. Okay, we get this. So what is the mechanism of this reaction? We have already seen. What is the mechanism of this reaction? Say step one. Step one is heterogeneous cleavage. Heterogeneous cleavage of CX bond to form tertiary carbocation. Okay, tertiary carbocation. This is step one. And step two is the reaction of the tertiary carbocation with the nucleophile. Okay, with the nucleophile to form the product. Okay, so this is the first step, this is the second step. So this is sequence means first this, second this, in some cases maybe third this, fourth this, fifth this, like that. প্ৰথমতে এইটো ৰিয়েকশ্যন হৈছে, নেক্সট এইটো ৰিয়েকশ্যন হৈছে, আন কিছুমান ৰিয়েকশ্যনৰ ক্ষেত্ৰতো আৰু ষ্টেপ থাকিব. এই যে ছিকুৱেঞ্চ, প্ৰথমতে কোনটো হৈছে, তাৰপিছত কোনটো হৈছে, এইটো ছিকুৱেঞ্চ অফ এলিমেণ্টাৰী ষ্টেপছ. আৰু মেকানিজিমত থকা গোটেইকেইটা ৰিয়েকশ্যন, each of the reactions in the mechanism is elementary reaction. মেকানিজিমত থকা গোটেইকেইটা ৰিয়েকশ্যনে হৈছে এলিমেণ্টেৰী ৰিয়েকশ্যন। গতিকে ইন ফিজিকেল কেমিষ্ট্ৰি ৰিয়েকশ্যন মেকানিজিম মিনছ সিকুৱেঞ্চ অফ এলিমেণ্টেৰী ষ্টেপছ। অ'কে, elementary reactions. Elementary reaction sequence. First this, second this, like this. So this is what we mean by reaction mechanism in physical chemistry. Now, second thing is how to determine the mechanism. How to determine the mechanism. Determine the mechanism. Mechanism of this reaction is this. Once again, in physical chemistry, mechanism of this reaction is this. Okay, so how we ascertain that mechanism of this reaction is this. Okay, for that what we do, we first propose some steps, elementary steps as the mechanism of the reaction. Okay, so this is the first step. We will propose some steps as the mechanism of the reaction. Next is that from these steps we try to find out the experimental rate law. Okay, from the proposed steps we try to get the experimental rate law. Okay, আমি যিকেইটা ষ্টেপ মেকানিজিম হিচাপে প্ৰপ'জ কৰিম সেইকেইটাৰ পৰা আমি এক্সপেৰিমেণ্টেল ৰেট লটো পাব চাম। এণ্ড ইফ উই গেট দি এক্সপেৰিমেণ্টেল ৰেট ল ফ্ৰম দি প্ৰপ'জড মেকানিজিম, দেন উই একচেপ্ট we accept the proposed steps as the mechanism of the reaction. Okay, I repeat, if we get the experimental rate law from the proposed steps, then we accept the proposed steps as the mechanism of the reaction. So these are the two main things. Okay, now number one, how to propose the mechanism. Okay, actually for determination of the mechanism there are two methods are there. In order to determine the mechanism of the reaction, there are two methods. One is rate determining step approximation method. And the other is the steady state approximation method. So there are two methods: rate determining step approximation method and steady state approximation method. Okay, now steady state approximation method, steady state approximation method. So there are two methods: rate determining step approximation method and steady state approximation method. Okay, now steady state approximation method. So there are two methods: rate determining step approximation method and steady state approximation method. Okay, now Let us first discuss about rate determining step approximation method. Rate determining step approximation method. Step approximation method. Let us first discuss about this. Okay. So in this method, how we propose the mechanism. First, in this method, how we propose the mechanism. Okay. So how we propose the mechanism? We propose the mechanism like this. Okay. Number one is that in the mechanism, okay, in this procedure, in this method, how we propose the mechanism. Okay. So number one is that in the mechanism there should be a first equilibrium. In the mechanism there should be a first equilibrium. Okay. First equilibrium means there is forward reaction, then there is backward reaction, and these two reactions, suppose A plus B, C plus D. So this is the first step. This is the first step in the mechanism. Okay. There should be equilibrium. Okay, equilibrium. And these two reactions, forward reaction, backward reaction, these are very, very fast reaction. Say rate constant is say K1, rate constant is say K minus 1. So rate constants are very high. That means both the reactions are very fast. Okay. So in the mechanism, first there should be a first equilibrium, or we can say like this. There should be a reversible reaction. Which is very close to equilibrium. We may say like this. We may say like this: reversible reaction which is very close to equilibrium. Or fast, okay, fast reversible reaction which is very close to equilibrium. We may say like this also, okay. And in the mechanism, this is the first step. Second step is that there should be a slow reaction. That means first equilibrium is followed by a slow reaction. Okay, slow reaction. Okay. So suppose these are the products, and from this, say rate constant is this, say E. Okay. And this reaction is slow. So first equilibrium which is followed by a slow reaction. That means rate constant is smaller. This is slow reaction. Okay. And third step should be the slow reaction is followed by a fast reaction. Slow reaction is followed by a fast reaction. Okay. That means say from E we are getting F. Rate constant is say K3. And K3 is once again, value of K3 is once again very high, much higher than K2. Okay. Value of K3 is much higher than K2. That means this reaction is very fast. So I repeat, in the rate determining step approximation method, how we propose the mechanism. Number one, there should be a first equilibrium, or we can say like this: there should be a fast reversible reaction which is very close to equilibrium, like this. Okay, K1, K minus 1, very high, very high. And second step is that this fast reaction should be followed by a slow reaction. Value of K2 is smaller. Third step, the slow reaction is followed by a fast reaction. That means again K3 is much higher than K2. So there may be some other steps also, but at least these 3 steps should be there, but not always. But rate determining step approximation method requires that the mechanism should have at least these 3 steps. There may be some more steps also, but it should, preferably the mechanism should consist of these 3 steps. Rate determining step approximation. Let us take an example. So you know aromatic primary amine C6H5NH2, aromatic primary amine. And when aromatic primary amine reacts with nitrous acid, say HNO2, nitrous acid, okay? And once again I put another hydrogen ion, that means acid, nitrous acid. What we get? We get diazonium salt. C6H5N2, diazonium salt plus H2O. Okay. Now this reaction is catalyzed by bromide ion. This is aromatic primary amine, nitrous acid. We get diazonium salt and of course water. Okay. So this is the reaction. Now if you apply law of mass action, do you remember law of mass action? If you apply law of mass action, what should be the rate law? Law of mass action. According to law of mass action, R should be equal to, say, K into concentration of C6H5NH2 HNO2 H plus. It should be this. Okay? But experimentally it is found that R equal to some constant into H plus HNO2 and Br minus. So this is the rate law. Okay, this is the rate law. So clearly, law of mass action does not agree with rate law. Okay, so immediately what you can say, this reaction is a complex reaction. Okay, rate law, that is experimental rate law, does not agree with law of mass action. That means this is not correct. Correct thing is this. This is the correct thing. And since experimental rate law does not agree with law of mass action, so what we can say? We can say that this reaction is a complex reaction. So since this is a complex reaction, it will have mechanism. Okay. Now according to rate determining step approximation method, how we propose the mechanism? According to this method, how we propose the mechanism? There should be a fast equilibrium, rapid equilibrium. So step one, rapid equilibrium, and that rapid equilibrium is this. This is fast, very fast, okay? Very fast equilibrium. Rate constant is say K1, K minus 1. Minus 1 means backward, okay? This is fast equilibrium. This is the first step, okay? There should be a fast equilibrium, and this is the fast equilibrium. And second step, what should be the second step? First step is followed by a slow reaction, okay? This slow reaction is this. K2 ONBR plus ONBR plus H2. This is slow reaction. So fast equilibrium followed by a slow reaction. Then what is the third step? The slow reaction is followed by a fast reaction. What is the fast reaction? ONBR plus C6H5 NH2 K3 rate constant. So C6H5 N2 plus H2O plus Br minus, so fast, okay? So according to rate determining step approximation method, there should be at least these three steps: fast equilibrium followed by a slow reaction, that is followed by a fast reaction, So this is how we propose the mechanism by using rate determining step approximation method, okay? Approximation method, okay? We propose the mechanism. After proposing the mechanism, what we do? We assume that the slowest step is the rate determining step. Slowest step is the rate determining step. So here, this is the slowest step, so this is the rate determining step. What does it mean? That means speed of this reaction is equal to speed of the overall reaction, okay? Speed of this reaction is equal to speed of the overall reaction. That means rate of the rate determining step is equal to the rate of the reaction, okay? That means rate of this reaction is equal to rate of the rate determining step. Rate of this reaction, speed of this reaction is equal to rate of the rate determining step, okay? Say মই এটা এক্সাম্পল দিব পাৰোঁ। সে আমি বটল এটাত কিবা বস্তু ভৰাব লাগে, বটল এটাত কিবা বস্তু ভৰাব লাগে, এনেকুৱা বটল এটা আছে, বটল এটাত আমি কিবা বস্তু ভৰাব লাগে। আমি কিমান ডাঙৰ বস্তু ভৰাব পাৰিম সেইটো কিহৰ ওপৰত নিৰ্ভৰ কৰিব? বটলটোৰ মুখখনৰ ওপৰত। বটলটোৰ মুখখন যদি ডাঙৰ হয় আমি ডাঙৰ বস্তু ভৰাব পাৰিম, okay? Just like that, this This reaction is the bottleneck reaction. This reaction is the bottleneck reaction. That means speed of this reaction will depend on the speed of this reaction. Speed of this reaction will depend on the speed of this reaction. This is just like bottleneck. Okay. So let us now apply this. So what is the rate of the reaction? Let me write it as R. What is the rate of the reaction? Rate of reaction R equal to rate of the rate determining step. What is the rate of the rate determining step? According to law of mass action, these are all elementary reactions. So we can apply law of mass action. We cannot apply law of mass action to complex reaction, but we can apply law of mass action to elementary reactions. Okay. So if we apply law of mass action, so R should be equal to K2 into H2NO2 plus Br minus. Okay. Now you see, so rate of the reaction should be equal to rate of the rate determining step. What is the rate of the rate determining step? This. Okay. Now here you see, this is neither reactant nor product. Okay. So we have to replace it by reactant. This. How to do that? Now from step 1, okay, this is equilibrium. So if we write equilibrium constant, okay, that means Q1, what is equilibrium constant? Equilibrium constant equal to rate constant of the forward reaction by rate constant of the backward reaction. This is equilibrium constant. Okay, equilibrium constant. So if we write this, what we get? We get concentration of H2NO2 plus divided by concentration of H plus and concentration of HNO2. Okay, so we get it. Hence concentration of H2NO2 plus, that is equal to K1 K minus 1 H plus HNO2. Okay. Now we are getting the value of this. So we can replace this value here. This is a number 1. Okay, this is number 1. So from 1 what we get? R equal to K2 K1 K minus 1 H2NO2. So H plus HNO2. Okay, we have written this. Then there is bromide. And these are constants. Okay. R equal to, this is K2. So K2, K1, K minus 1, these are constants. So I can replace this by another constant. So for this, I am writing K, H plus HNO2 and Br minus. Okay, R equal to this. And we are getting the experimental rate law. You see, we are getting the experimental rate law. Okay, we are getting the experimental rate law. So we can say that our proposed mechanism is okay. Since we are getting the experimental rate law, from the proposed mechanism, so we can say that our mechanism is okay. So this is rate determining step approximation method. Okay. Now let us talk about the steady state approximation method. Okay. Let us talk about the steady state approximation method. Steady state approximation method. Steady state approximation method. Now, here what happens? No doubt we will propose the mechanism like this, but there is no need that there should be equilibrium. Steady state approximation method does not need that there is no question of equilibrium. Okay. So number one thing is that equilibrium is not necessary. Not necessary. Maybe there, but not necessary. Not necessary. Then second thing is that we are not interested in fast, slow like that. Okay? Not interested in fast, so not interested in fast, slow, etc. Okay? So these are not required at all. So what is required is that say here, so for this reaction, let us use the same reaction. For this reaction, we are writing the mechanism like this. So in steady state approximation method, we does not require equilibrium. Neither we require fast, slow, etc. We will just propose some steps as the mechanism. Okay, there may be reversible reaction. There may be reversible reaction, but not necessarily equilibrium. Okay, and fast, slow not required. Number one. Now here you see in the mechanism this species, okay. So these are the two species which are neither reactants nor products. These are intermediates. Okay, these are intermediates. So in steady state approximation method, we have to identify the intermediate first. I repeat, in steady state approximation method, we have to identify the intermediate. We have to identify the intermediate in the mechanism. So here in this mechanism, these are the two intermediates because they are neither reactants nor products. Okay, these are the intermediates. Now, in this steady state approximation, we assume that intermediate concentration will be very low. Intermediate concentration will be very low. Why? Because they are highly reactive. Once this is formed, this will at once react. Okay, once this is formed, this will at once react. Okay, that means intermediates are highly reactive species. Since these are highly reactive, so as soon as these are formed, they will immediately react. So obviously, concentration of the intermediate will be small. concentration of the intermediate will be small. Okay, so and in steady state approximation we assume that d intermediate dt, d intermediate dt is 0. We assume this. And by assuming this, we try to find out the rate law from the proposed mechanism. Okay? So by assuming this, we try to find out the rate law. Okay, rate law. So basically this d intermediate dt equal to 0. We propose this. Okay. Now statement of the steady state approximation. Statements of steady state approximation method. Statements of steady state approximation method. Statement of the steady state approximation method. Okay. If an intermediate in a reaction mechanism is highly reactive, each concentration will be small. That is, concentration of intermediate will be very, very small than the concentration of the reactant or concentration of the product. It will be very, very small. Concentration of the intermediate will be very, very small than the concentration of the reactant or product. So after a certain lapse of time, called the induction period. That time is called the induction period. Tau. After a certain lapse of time, after some time, okay, and that time is called induction period. After the intermediate concentration generally behaves as a monotonic function of time. Okay. What is monotonic function? Say, let us discuss about. Let us see the graphs of this, just like this. Say this is the reaction, consecutive reaction. Here this is the intermediate. Okay, This is the intermediate. This is the intermediate. So if you remember the graph of the intermediate, say concentration of B, so I am plotting concentration versus time. So for A, the graph was like this. Okay. For concentration of A, the graph was like this. Okay. This is for A. For C, the graph was like this. For C, the graph was like this. This is for C. And for B, the graph is like this. The graph is like this. The first increases, reaches maximum. First increases, reaches maximum, then decreases. Continuously decreases. Monotonic function means either continuously decreases or continuously increases. There is no like this. Okay? So continuously decreases. That is monotonic function. Or continuously increases. That is monotonic function. Okay? There is no fluctuation. That is a monotonic function. So now concentration of B, this is for B. Red one is for B. So concentration of B is very, very small. This is very, very small. This concentration is very, very small. So this is the induction period, tau. Induction period. So after first increases, then it becomes a monotonic function. Decreases, continuously decreases. Okay? After certain lapse of time, this time, concentration of B becomes a monotonic function of time. That means continuously decreases. Okay? Continuously decreases. Now since this concentration is very, very small, so this decrease will be very, very small. Since concentration of B itself is very, very small, এই বস্তুটোৱে অতি কম মই ইয়াত ডাঙৰকৈ দেখুৱাইছোঁ বাট দিছ ইজ ভেৰি স্মল সেইকাৰণে এই ডিক্ৰিজ হোৱাটো কি হ'ব এইটো আকৌ স্মল হ'ব দিছ ইজ ভেৰি স্মল অ'কে ভেৰি স্মল দেট মিনছ concentration of B can be thought as constant because decrease hoise no doubt কিন্তু very small decrease hoise so concentration of B to আমি constant বুলি ধৰিব পাৰোঁ constant বুলি ধৰিলে কি হ'ব so for t greater than tau okay greater than tau d intermediate let me write it like this I means intermediate okay let me write it like this I means intermediate so di by dt will be very small okay and in steady state approximation what we do in steady state approximation method what we take di by dt to be 0 we take this 0 for t greater than tau okay because this decrease is very very small so we can assume that as if this is constant so as if this is constant so di by dt will be 0 and that is for time greater than tau okay this is the statement of steady state approximation method okay steady state approximation method now so let us see the same reaction Let us see the same reaction according to steady state approximation method. Same reaction according to steady state approximation method. Now, what is the difference from rate determining step approximation? What is the difference? There is no question of equilibrium. There is no question of fast flow. Okay. So this is the product. This is the product. Okay. This is the product of the reaction. This is the product of the reaction. This is the product of the reaction. Okay. Now, if we write rate definition, if we write definition, from definition, if we write rate of the reaction, from definition, okay, now what we are going to do? We are going to apply application of steady state approximation method. Okay, for the same reaction. Okay, for the same reaction. Now, from definition, rate of the reaction, from definition, rate of the reaction equal to minus d concentration of this by dt equal to minus concentration of this by dt. Okay, then this, then equal to plus d concentration of this by dt equal to half and this. Okay, so from definition, what is the order of the rate of the reaction? Minus d C6H5 NH2 by dt equal to minus d HNO2 by dt, then minus dH2, then this is equal to d C6H5 N2 by dt, then this is half d H2O by dt. Okay, so from definition, rate of this reaction is this. Okay, we have already seen this, no problem. Now let us consider this. This is the rate of the reaction. Let us consider this. This is the rate of the reaction. Okay, now in the mechanism, we have diazonium salt here. We have diazonium salt here. So if we write rate of reaction, d concentration of this by dt will be equal to K3 into this, concentration of this into concentration of this. Okay, now from mechanism, okay, from mechanism, I am taking this R equal to d C6H5 N2 dt, that will be equal to K3 concentration of ONBR, okay, concentration of this into concentration of C6H5 NH2. Okay, this, you see, mechanism, d this equal to K3 into concentration of this into concentration of this. Okay, this. So this is a number 2. Okay, this is number 2. This is number 2. Okay, so we have written this. So rate of this reaction, rate of the reaction equal to this. Now here you see this is intermediate. This is intermediate. Okay, so now what we do? We write DONBR dt. because the rate law does not contain intermediate. Rate law does not contain intermediate. So what we write? d(u(n)br dt. Now from the mechanism d(u(n)br dt, d(u(n)br dt. Now here you see, in this reaction, this is formed. This is the product. Product means K2 into this is plus K2 into this. Okay. Now this is reactant. In this reaction, ONBr is the reactant. Here ONBr is the product, but here ONBr is the reactant. So if this term is positive, here this term will be negative. Okay. So K2 into H2NO2 plus Br minus. So this is positive because product. Now this is negative. This is a number 3. Okay, this is number 3. Now once again we are getting another intermediate. Okay, we are getting another intermediate. So now we will write d intermediate dt. Okay, so d H2NO2 plus dt. This. So this is equal to what we get? Again, forward reaction, this is found. Backward reaction, this is lost. This reaction, this is lost. So positive, negative. Now for this reaction, reactant is this. For this reaction, reactants are this. But for this reaction, reactant is this. Okay. So positive formed, positive, lost, decreases, concentration decreases, negative, concentration decreases, so negative. So it will be, you see, K1 into H plus HNO2 minus K minus 1 H2NO2 plus. Okay, H2NO2 plus. Backward reaction. For the backward reaction, reactant is this. Okay, reactant is this. So minus. Then minus. Again minus K2 H2NO2 plus. Then Br minus. Okay, this is number 4. So these are the equations we are getting. Okay, now from 3 what we get? D intermediate dt equal to 0. So this is equal to K2 H2NO2 plus Br minus K3 ONBr C6H5NH2. Okay, C6H5NH2 or ONBr equal to concentration of ONBr equal to K2 H2NO2 plus Br minus then K3 C6H5NH2. NH2. So we are getting this. But here again we have this, so we have to replace this. This is intermediate, so we have to replace this. So from 4, what we will do? From 4, again the intermediate dt 0. Okay, so this will be equal to, let me write it like this. This will be 0. Okay, this will be 0. So K1 H plus HNO2 equal to K minus 1 H2NO2 plus K2 H2NO2 plus Br minus. Okay, and this is equal to, if I take this common, H2NO2 plus, so this will be K minus 1 plus K2 Br minus. Okay, hence H2NO2 plus, this will be equal to K1 H plus HNO2 K minus 1 plus K2 Br minus. Okay, we are getting this. So so then this is a 5. Okay, 5. So from 5 what we get? ONBR equal to K2, let me write it like this, Br minus K3 C6H5NH2. okay, K2, then this is equal to K1H plus HNO2 K minus 1 K2 Br minus. Okay, so this ONBR equal to this, then we have written this. Hence rate of reaction. What is rate of reaction? Rate of reaction is this. Rate of reaction is this. So from 2 now from 2 rate of reaction equal to K3 into ONBR equal to this. So K3 K2 Br minus K3 C6H5 NH2 K1 H plus HNO2 K minus 1 this. Okay, so we have written ONBR K3 ONBR. So we have written ONBR, then we have C6H5NH2 C6H5NH2. Okay, now here cancels. So what we get? K3 cancels. So what we get? We get K2 K1 H plus HNO2 Br minus K minus 1 plus K2 Br minus. Okay, R equal to this. So according to this state approximation, this is the rate law. according to steady state approximation, this is the rate law. Okay, so rate law according to steady state approximation. Now here if we assume, no, if we assume say k minus 1 to be greater, very greater than k2 br minus, then what we get? So if we assume this to be very greater than this, so we can neglect this. Okay, we can neglect this. If we assume that this is very greater than this, so we can neglect this portion. Then what we get? R will be equal to k2 k1 by k minus 1 h plus HNO2 Br minus. Okay, and that is equal to say k H plus HNO2 Br minus. So you see, we are getting this if we assume this. So okay, all right. So here you see, we have not talked about any fast slow reaction. What we have used? We have used d intermediate dt equal to 0. We have used that, nothing else. Okay, so I repeat. So in order to apply steady state approximation, what do we do? So first we write from definition what is the rate of the reaction. Okay, then for anyone, I may take this, anyone. For anyone, I write the expression. Anyone, not necessarily. Etu nohoy je tumi okol yakhe lobo lagibo, hetu nohoy. Moi etu loisu kyo, just to avoid minus sign. Moi etu product loisu. Okay, you can take this also, no problem. Okay, but for convenience, I have taken this. That's all. Okay, so let us see one or two examples of steady state approximation method. Okay, let me see. So question is this. For the reaction 2NO plus Cl2 2NOCl, the mechanism is first step is that NO plus Cl2 K1 K minus 1 NOCl2, and the second step is that NO plus NOCl2 K2 2NOCl. Okay, now apply steady state approximation. Method to show that R equal to KNO2 Cl2, assuming K2NO to be very less than K minus 1. So this is the question. Okay, mechanism has been given and you have been asked to apply steady state approximation method. Okay, We have been asked to apply steady state approximation. Now, how to do it? Say, what is the rate of this reaction according to definition? According to definition, what is the rate of the reaction? Rate of the reaction equal to half dNO dt minus equal to minus dCl2 dt equal to half dNOCl dt. Okay, so according to definition, rate of this reaction equal to this. Okay, now let me write this. Okay, let me write this. So dNOCl dt from mechanism. Okay, this is from mechanism. From mechanism, if we write this dNOCl dt, okay, equal to K2 concentration of NOCl2. Okay, now here you see this is a number 1. Okay, this is number 6. Now here this is the intermediate. Okay, this is the intermediate. So we have to write intermediate, d intermediate dt, and that is equal to, so you see this is the mechanism. So formed NOCl2 formed, NOCl2 lost. Formed means positive, negative. Okay, so this will be equal to K1 NOCl2 minus K minus 1 NOCl2, because backward direction reactant is NOCl2. Okay, then this minus K2 NOCl2. Okay, K2 this. Alright, now steady state approximation method. According to steady state approximation method, so d NOCl2 dt is 0. Okay, 0. So K1 NOCl2 equal to K minus 1 NOCl2 plus K2 NOCl2. Okay, this is equal to NOCl2 K minus 1 plus K2 NO. Okay, hence NOCl2, that is equal to K1 NOCl2 K minus 1 K2 NO, K minus 1. Okay, so we have got the value of NOCl2. Now from 6, what we do? From 6 we put R, d NOCl dt. Okay, d NOCl dt equal to K2 NO into K1 NOCl2 K minus 1 K2n. Okay. Now, what is the condition we have been given? This is very, very less than this. Okay. This is very, very less than this. So we can neglect this. No? Since K2NO is very, very less than K minus 1. So dNOCl dt equal to K2NO K1NO Cl2 K minus 1, and that is equal to K2 K1 K minus 1 NO square Cl2 or we can write half dNOCl dt equal to half into K2 K1 K minus 1 NO square Cl2, and that is equal to K into NO square Cl2, and this is nothing but R. Rate of the reaction. Okay, R equal to half this. Okay, so we are getting this. So put. Okay, so you have to do like this. So we can see another example. Okay, or I can give you a few examples. You can try to solve. Okay. Let me see. Okay. Next question 1. Okay. For the reaction 2NO plus 2H2O plus N2 mechanism proposed is first step NO plus NO K1 K minus 1 N2O2 plus H2 K2 N2O plus H2O N2O plus H2 K3 N2 plus H2O. Okay, so this is the mechanism. Assuming K1 very, very less than K2H2, show that R equal to K NO square H2, and apply steady state approximation method. Okay, so this is one question. Then let me see another question. for the thermal decomposition of O3 mechanism is O3 step 1 O3 K1 K minus 1 O2 plus O. Step 2 O3 plus O K2 2 O2. Apply steady state approximation method. To show that minus dO3 by dt equal to K O3 square KO3 square by O2 assuming K minus O2 is very greater than K2O3. Okay, assuming this. So this is there is another problem. Let me write all the problems. 3 okay, so you try to solve these two problems, and if you can, it is very good, and if you are not able to solve these two problems, then you let me know, I can help you. Okay, after this we will discuss another topic which is known as chain reaction. Okay, so today let us stop here. Thank you.